Good morning. This video is the second video in section 3.4. The topic today is inflection points. There will be one more video in section 4 on Monday. So, all right, let's talk. We're defining what an inflection point is, and the distinction here is keeping straight an inflection point versus a critical number. So this says any point on the graph of f of x is an inflection point if the concavity changes at that point. This can only happen at a point where the second derivative, and I can spell second, I promise, where the second derivative is either equal 0 or is undefined. Now, we did this already. Yesterday, when we were finding concave up and down intervals, we found the second derivative, and we figured out where it equaled 0 was undefined. And then we made a table, and from that, we determined intervals of concave up and concave down. All we're doing here is kind of concluding something from all that work. And so any point where the concavity changes is called an inflection point. Okay. Now, there's an important, as it says in this slide, there's an important distinction between first derivatives and second derivatives as far as critical numbers versus inflection points. So let's review here. For the first derivative, you'll recall all of the points where the first derivative either equaled 0 or was undefined, we called those critical numbers. Didn't matter if there was a max or a min there, all of those points were critical numbers. And then from the table that we made, we were able to determine if there were any maxes and mins. And the maxes and mins could only occur at those critical numbers. But again, every point on the graph, or every point where the first derivative equaled 0 was considered a critical point, whether or not it was a max or a min. So to remind you, if a graph looks like x cubed, turns out that there is a horizontal tangent at 0. So you take the first derivative and set equal to 0, you would get 0 as a solution. So 0 is absolutely a critical number, but it's increasing until 0 and then increasing after 0. So there would not be a max or min. That was fine for the first derivative. Like, again, the distinction is when you find the points where the first derivative equals 0 or is undefined, they are all critical numbers. And then you take those critical numbers and figure out which of those, if any, are maxes or mins. For the second derivative, you're still going to take the second derivative, and you're still going to find the points where it's undefined or where it is 0. And you're still going to then make that table and find concave up and down intervals. All that we did that yesterday. But if it's an inflection point, it has to be a point where the concavity changed. Like if the concavity is up on one side and up on the other, then it's not an inflection point. So that's different. So just again, all the points where it equals 0 or isn't defined are not necessarily inflection points, only if the concavity changes. And then the other distinction is this last one. The function actually has to exist at an inflection point. It can't just be at an asymptote. So in particular, this picture right here, where did I draw it? I drew it here. So there's just a rational function that has an asymptote. And clearly from negative infinity to 3, it's concave up. And from 3 to infinity, it is concave down. So if you're making a table, which you would make for this, at 3, it would be concave up on one side and concave down the other. But this would still not be an inflection point because there's actually no point on the graph. The inflection point has to be an actual point on the graph. So you just got to be a little careful which ones you call inflection points. It's a point on the graph where the concavity changes. So the good news is what you've done so far in this section where you found first derivative, then you found the second derivative, then you found where it equals 0 or is undefined, and you made a table, and from that defined intervals of concave up and concave down. We're doing all that again. We're just at the end adding the identify any inflection points. So I'm just going to do one example with you. It looks like this. So, and I did some of the work here just to save us some time. It says find concave up and down intervals and identify any inflection points. So the cubic is y equals x cubed minus 9x squared plus 24x minus 18. I went ahead and already found the first derivative, which was 3x squared minus 18x plus 24. And I found the second derivative, which is 6x minus 18. All right. So clearly we need to know where that second derivative either equals 0 or is undefined. So I set that second derivative equal to 0, and I get x equals 3. So that's the potential inflection point. So now, again, so far this is the same as yesterday's assignment. I am going to make a table, and I've started the table here. My intervals go from negative infinity to 3 and from 3 to infinity. I need to test a value, and so I'll pick I don't know, 0 there and 4 there. And we are finding the sign of the second derivative. So my second derivative was what? It was this, 6x minus 18. That was my second derivative. Well, if I plug in 0, I get 0 minus 18, which is negative 18, which in particular is negative. And if I plug in 4, I get 6 times 4. 24 minus 18 is 6, which is positive. So this is concave up from 3 to infinity. And it's concave down from negative infinity, oh dear, to 3. And as far, is there an inflection point? Since the concavity changes at 3 and the function exists at 3, so yes, there is in fact an inflection point at x equals 3. And again, the question might give you, if it asks for like at what point is the inflection point, like if it wants the whole order pair, you of course would have to plug 3 back into the original function, which I'm not going to do right now since telling me that the inflection point occurs at x equals 3 will suffice. But if the answers happened to be ordered pairs, you'd have to take 3 and plug it into that, which is a big enough number. I'm not going to worry about that. But it's possible you might be asked that. So that's the process for finding inflection points. It's just everything you did yesterday. And then if there's an x value where the concavity changes, and if the function exists at that point, that is considered an inflection point. So it's a very common question. Here's a function, find the inflection points. I think your homework actually asks for both concave up intervals and down intervals and inflection points. So that is it for this video. Your homework is 15 to 33 on page 242, where the instructions, let me clarify them, they say find the points of inflection, and it says discuss the concavity. It's a stupid phrase. Just give me intervals where it's concave up and intervals where it's concave down. All right, that's it. Have a great Friday. And then there'll be one last section on 3-4 on video with 3-4 on Monday.